Good afternoon, everybody. My name is Steve Clifford. I'm the head of the CIBSE Healthcare Group. Thank you for joining our webinar this afternoon. The webinar is going to be presented by Professor Darren Woolf of the Worth Research Group, who is going to present on understanding airborne reduction in buildings. Just as a matter of interest, Darren is also head of the building simulation group from CIBSE as well. The presentation will be recorded and be loaded up onto the healthcare website. And if you've got any questions, if you could put them in the chat box as they go along, and then we will pick them up at the end of the talk. So I now hand you over to Darren Woolf. Thank you very much, Darren.
Thank you, Steve. Thank you for the introduction and inviting me to give this talk. So I'll be talking about understanding airborne infection reduction in buildings. To start with, I'd like to give a sort of brief overview of my airborne infectious diseases journey. So back in SARS 2003, I was involved in looking at the low-level extracts in hospital wards and how to capture some of the larger droplets. Then looking at UV tubes, different arrangements of UV tubes and how they kill air passing over those tubes. And then from the Hong Kong high-rise focus, looking at air movement through dry traps in toilets. Then there was CDIF 2007, where I helped on the thermal and airflow side, two PhDs, and they had a focus on hospital wards. And now, if we jump to more recent history, in May 21, as part of the CIBSE Building Simulation Group, we had a joint event with CIBSE England, estimating airborne infection through simulation and analysis. And then more recently, in March this year, we published the Airbods Guide, Findings and Guidance for Airborne Infection Resilience. That was part of a 2-year research program, Airbods being airborne infection reduction through building operation and design. And then in April this year, as part of my Worth research work, we've been doing a number of exercises in our open air initiative, and there was a building environment paper, a CFD based framework to assess airborne infection risk in buildings. So today I'm going to be talking about all three of those aspects, and I'll be referencing really heavily the BSG CIBSE event, the Airbods Guide and the B&E paper. So quick introduction to Airbods. The Airbods programme was 6 universities and Worth Research. It was led by Loughborough University. It was organised into 4 work packages, experiments, modelling, case studies and design guidance and dissemination. And today I'm going to be talking about measurement and calculation methods in some detail. We did talk a little bit about dynamic thermal models in Airbods, but it was mostly about monitoring, test chamber, analytical and CFD based research. So the Airbods Guide, as I said, it was launched in March this year. You've got a theme on every single page. You've got the theme and one subject per page. You've got mostly bullet points, so it's about easy readability, easy access. So it's industry facing, and there's some research, some references that you may wish to follow up on, but all the Airbods references in the full material you can get on the website. And then there's some additional material. There are some other research programs we knew CodeTrace well, which was focused on schools. Our research assistants had joint seminars with the CodeTrace research assistants. There's Protect as well. There was a more recent guidance, such as ASHRAE Standard 241 on control of infectious aerosols. And as part of the marketing of that, just very recently, there's a YouTube podcast. I recommend that if you're going to get into ASHRAE Standard 241, you go to the podcast to start with. And by the way, when you get these slides, the PDF of these slides, there's a lot of embedded links. So you'll be able to hopefully just click and go. And then there's a lot of research, some PhD just coming out recently on spatiotemporal uncertainty, which is what I like to think about a lot. It's about bridging between thermal models and CFD using statistical approaches. There's articles such as in the CIBSE journal, Hospital Indoor Air Quality, which was recent, and Royal Society papers, and many, many, many more. So when we talk about airborne infection reduction, you may be wondering, why isn't it about assessing or quantification or prevention or reduction? So if we think about quantifying risk, there's a huge uncertainty related to the viral load, what's breathed out, and infectious dose, what's breathed in. This graph here is just a sort of schematic, but obviously if you apply that to any particular population in a particular room to actually catch what's actually going on with the breathing as well, which is highly dynamic. It's not a static act, not just breathing out CO2, but all the various droplets and aerosols as well, and singing, speaking, talking. So it's quite it is a very, very dynamic arrangement of different sources within a room, and also there's a complexity associated with droplets and the ambient environment. So it's very almost impossible to quantify risk. And there's preventing risk. You see prevention of diseases quite often. There's no 100% cure solution. This again is an absolute term. It gives a sense of safety where perhaps that may not exist. So reducing risk and airborne infection reduction, this is a relative term. It recognises these uncertainties and complexities and quite often cancels out with the approaches that we use. And obviously these relate to human ventilation and other building related factors. So the focus is really on comparative qualitative assessments over quantitative, and we know we can deliver them with high levels of confidence. And this is reflected in many of the calculation methods. So air kills or can seriously damage your health. Sounds like something off the back of a cigarette packet or something like that, but it's true. If you look at the National Risk Register, where it's plotting impact against likelihood, pandemic is the top risk out of 63 listed, and emerging infectious disease is not far behind that. And some of the many often related areas to consider are things like aerosols, gaseous and particulate matter, mold, other indoor air quality such as VOCs. And then there's the headlines as well, such as climate and air quality crisis, net zero, the ULEGS extension, and the victims, such as Ella and AWAB, which again hit the headlines, and they're not the only victims. There's the silent victims in their many, many thousands as well that may have contributory factors to their health or even to their death. So a quality ventilation mindset is needed, and that includes the elements of effective and efficient delivery. So the Ventilation Juggling Act, we've got Guide A, Guide B from CIBSE, natural ventilation, AM10, mixed mode ventilation, AM13, Health and Safety Executive, looking at contaminants, approved document F, and all the references there, and it starts to bring in other areas such as indoor air pollutants, cross-referencing to other parts, cross-referencing within those documents to other documents, some of them over 20 years old. Then coming out of the pandemic, we've got more recent guidance from UK side. If you look at ASHRAE 241, it talks about these being the prerequisites to applying 241. It's talking about hopefully these may become part of the air quality standards within ASHRAE. If you listen to the podcast, you'll see more on that. Then we've had the Building Safety Act, which came into force earlier this month. So the Building Safety Regulator, it's about safety and performance for all building works. There is a special high-risk building focus, fire and structural safety focus, and that's a basis for height of the building plus having a residential unit. So what's the next iteration going to be? Is it going to be, for example, care homes on a ventilation basis? If it is going to be something like that included, plus many other areas, we need to start to think about that now. So the risks, there's multiple sources, many priorities, conflicts, potentially emissions, over complexity, and this question of reasonable competency. What do we mean by reasonable competency? Would we expect a grad +4 to have to navigate through all these various documents and find out what's the most appropriate for them? So now a little bit on air mixing. So this guide at the bottom, a guide to energy efficient ventilation. It's quite old now, 1996. It's a great guide to get into ventilation. It's a free book that you can get online. And in the chapter ventilation efficiency, there's many other aspects within the book. It talks about air mixing. So you've got this no mixing, or this plug type flow, which is least common. You've got what's called perfect mixing, and this is often assumed within airborne infection metrics. There's many things that influence mixing, such as room configurations, distribution of infiltration paths, supply and extract grills, supply air characteristics, location, size of heat sources. But turbulence is something that quite often isn't captured at all in these models, right, in some of the analytical models. You might be able to be measuring in an environment the effect of turbulence, but you may not actually see it because it's hard to actually know what it's doing. But things like CFD could tell you how much and where. And then there's poor mixing zones, something that's not perfectly mixed. It's not a plug flow. This is possibly the most common. If you've got stagnation zones in a room, for example, it's infrequently considered, but it is a standard CFD output. So the air changes per hour, ACH conundrum. So if you've got this room, single height room, 3 meters high, 4 by 4 meters, it has a volume of 48 cubic meters. If you double the height to 6 meters, it has a volume of 96 cubic meters. That's a very simple equation which relates the air changes per hour as the flow rate in litres per second over the volume in meters cubed. So if we think about the first ventilation rate, 10 litres per second per person, so we do see that quite a bit. And if you just divide that by the floor area, it's 0.625 litres per second per metre squared. And if we look at the single room, that's 0.75 air changes per hour. If you double the height, it's 0.375 air changes per hour. If we now go to a separate ventilation rate, you quite often see 10 air changes per hour. And if you put that into the single and double height, you've got over 130 litres per second and 266 litres per second. So you've got well over a factor of 10 just moving from litres per second per person to air changes per hour in the room. So again, you double the height, you half the air change rate, and there's no change in the rate per unit area or per person. If we combine ventilation rates, we're used to these sorts of systems where we quite often focus on the supply airflow rate, W litres per second. If it's a balanced system, it might be W litres per second. You might get a minimum fresh air rate. Quite often, a number of us don't like using the word fresh anymore because outside might be polluted. but that would be your proportion, 0.2 W coming in from outside, and the same as that exhausted. And so that's a sort of classic central plant type arrangement. Then you might have an air cleaning device in there with a flow rate X litres per second in there. Then a recirculating air handling unit with Y litres per second there. And then you might have infiltration and exfiltration with Z litres per second there. So you may not be focusing on all the flow rates and the balances when we're looking at the flows in the room. And sometimes we combine these flow rates into like an effective ventilation rate based on the supply airflow rate and adjusted by the air clean device and recirculating air handling unit flow rates, maybe including a removal efficiencies factor in there. So it's not just about a flow rate in a room, there's lots of flow rates and there's effective flow rates. So this is the ventilation rate challenge. When we look at the defined rates and units, so there's these directly calculated or measured values, such as supply airflow rate, which you're used to seeing, natural ventilation rate, outdoor airflow rate. We'd quite often think of that about moving a volume per unit time, which is the units. Then there's the indirect or derived values that might have effective or equivalent before it, and there's a whole range of flow rates there. So what you need to do is understand the detail within each of those definitions. Go to source and understand what they're doing at equation level. Then there's units. So in guide A, it might be 10 litres per second per person, or an operating theatre up to 1,000 litres per second. Guide B, 5 for infiltration, 5 metres cubed per hour per metre squared of facade. Part F is talking about an additional measure of 1 litres per second per metre squared of floor area, and also a minimum percent of floor area to define a nat vent flow rate. And HTM 301, which I'm sure you're aware of, specialised ventilation for healthcare premises, talks quite often you see 10 air changes per hour. They're all doing the same thing. It's about defining a flow rate into a space, and it's essentially 6 different ways to do that same thing. So you need a laser focus on units, otherwise you will become unwittingly non-compliant, and you could be out by a factor of 10 or more. So more on the ventilation rate challenge, space types and sector rules. So space types, in the healthcare sector, there's a whole host of different specialist or critical ventilation systems that you may be interested in. Then there's all the other spaces, such as toilets, corridors, atria, cafes. And one approach might be to use ventilation typology and space grouping techniques in order to categorize those that are quite similar, including what ventilation systems are there. Then there's sector specific rules. So it might be the minimum air supply volume is to be the greatest of minimum fresh air, maximum heating or cooling, temperature differential or air change rate. Or there might be a few other things within there that you need to consider. So there might be 3 or 5 outputs for each room, covering a wide range of what we're trying to do, which is optimum ventilation strategies. So when we think about this ventilation juggling act and the ventilation rate challenge, I'm asking the question, is it time to go digital? CIBSE has been moving from paper guides towards digital guides. I'm not just talking about having digital guides, but we have a lot of tools that support the decision-making processes about what ventilation rate is appropriate for what type of space and what type of system. There are a whole host of ventilation performance metrics out there. You may have heard of ventilation effectiveness. This is a zonal version of it, where you've got a breathing zone and a supply zone. And depending on how, for those 3 systems that you've got there, depending on how the air is coming in and going out and what temperature differences are, you could pull out of a table what the ventilation effectiveness is. And it's showing here displacement can be above 1. So again, this is like quite zonal space specific, and it is quite simplistic, but it could be used to give you some early indications about ventilation performance. And this ventilation effectiveness, this is about estimating the efficiency that pollutant is diluted or removed. So it's like assume that it's throughout that particular zone, and it assumes that each zone is perfectly mixed. There are a separate stream of metrics, like the air change efficiency metrics. You may have heard of age of air before. That's a mean time taken for air molecules arriving from the domain to travel to the point of interest. And some of these metrics can just pop out of a CFD analysis. So what I'm suggesting on the back of the pandemic is whether we should re-examine the zonal metrics. I spoke to Martin Liddeman, who was the author of that ventilation book I mentioned earlier, and I asked him in chapter 9, there was all these hosts of other metrics like a local air quality index. What happened to them? And it was they just went out of fashion, I think, and some of the other metrics were taken up and run with. So maybe we need to start look at multiple metrics and some of the other metrics. I've got that slide up there. So that's a Nightingale Award. Just want to leave it up there. And what do you see when you look at that slide? Just give you 5 seconds or so. Okay, so now I'm going to share what I see. So I'm very immediately attracted to the corners. Are there cold wall surfaces drawing contaminated air at high level toward low level? So these surface buoyancy effects. Then I'm thinking, I don't exactly know from that picture where the high level probably air handling units are. We like to draw these nice arrows. That's not quite how it works. But does the background room airflow pattern support delivery of outside air to individual breathing zones? And then these screens. Are the screens making cross contamination or local conditions better or worse? I'll talk a little bit more about why it could be worse a bit. Then the bed positioning strategy to minimise cross-contamination. This isn't just where the beds go, but the timings of putting the beds in. Is it better to put them all in one area, or is it better to space them out? What's that strategy? Using breathing channels to improve ventilation performance. That's a key one for me. And also, you've got a high ceiling, so you've got this big reservoir. Is that a good or bad thing? We know that you'd have a limited ventilation rate within the given ventilation performance. Can that be utilised to our benefit? Perhaps putting extracts more at high level. So the challenge is to combine these different viewpoints and priorities into an all-encompassing strategic plan. So beyond ventilation, there's a load of different areas you could go if you wanted to go beyond ventilation. I've listed some of them there. I think a good starting point is the Airboard's Guide, chapter 2, where we, through bullet points, list a lot of the things such as the basics on environmental factors, how it affects droplets. And then you can't go wrong listening to Lindsay Marr's 101 on aerosol and transmission of respiratory viruses. But ultimately, you need to think who's going to do this work. Is it in-house expertise to get that deeper understanding, wider context, and possibly better solutions? If it is the case, then you need to give the time and the bandwidth for that to happen. Then you may need third-party support. And what's the cost of that relative to developing that in-house? And that would need to be maintain and development costs of the systems that you develop. Expert sign-off, that's a funny one, because what is expert sign-off? We haven't really got the targets agreed yet, and there is a confidence sign-off rather than an expert sign-off. No one will tell you that you're safe. So future guidance, I'm suggesting it should be simplified to ventilation performance on a need-to-know basis. and there'll be many defaults and scenario driven. If we're expecting people to go into this world, then it may just be a very limited number of people that actually bring airborne infection reduction into buildings. So I think we need to go down a different route and make sure that the experts translate that and communicate it well to the wider audience. Need to be prepared. So in the Airborne's guide, we got a load of feedback from focus groups in these areas, case studies focusing on theatres and restaurants. You might want to think about similar space types. We talk about rethinking ventilation design and operating plans for a pandemic, whether it's existing refurb or just changing operation. But ultimately, it's about budget and time resource. Where are the you need to organise the learning and training elements, selecting your operating design scenarios. Expectations is a key one. Making sure your starting point, inside out, and that might mean some measurements. And then there might be calculations and measurements that you need to carry out. The pandemic preparedness and operating plans is something that we talk about in the guide. And then the implementation monitoring and updates. So there's a whole host of things you need to do. Cost of not doing it, is it a reputational risk? Is it a critical business risk? There could be a whole host of things that go beyond the I'd just like to do this. So transmission paths guide mitigation solutions. So I pulled this from the CIBSE Air Cleaning Technologies guide. You've got the infected person on one side, you've got susceptible person on the other, you've got all sorts of things from the infected person and their activity, and the green things are all these mitigation solutions. But ultimately, you've got a transmission medium, and the transmission medium is the environment. And within that, you've got aerosols. So quite often we think about aerosols being this long range transmission. It's also short range as well. So short range transmission. So I put this in the category of medium to high transmission risk, but it's the highest risk of super spreading events. Then you've got the larger droplets. So this is short range airborne transmission. It's got high transmission risk, and it's reduced by physical distancing. I'm sure we're all aware of that. Then there's surface transmission. This is the lowest transmission risk, and it's reduced by cleaning. What's interesting is how cleaning. Why do we clean surfaces? I read a research paper recently about the reanimation of particles, virus particles off the floor. So it's. I'll talk a little bit about that later. So let's think about the relative position of a person or persons to room air movement. So you've got the ventilation airflows driven by your supply air grills, to a lesser extent your extract air grills. You've got surface temperatures. If the surface temperature is different to the air temperature next to it, then there'll be a flow over that surface. Internal heat gains, people, equipment and lights. So quite interested in surface to air and air to air buoyancy effects. And these could change by the hour, day and season. Then the person may move, not only change location, but change breathing direction. So how are they breathing that air into the background air movement, air pattern? And then you need an infection source as well, which may or may not have been in the room, and they may be moving as well. So it's quite a dynamic situation with lots going on. Perhaps the most static thing is the background air movement on an hourly by hourly basis. And we've got to try and come up with guidance so that we can say that this space is safer than it was before because the ventilation is better. So not as all as it seems. So you may say dividing screens reduce airborne infection risk. Well, that's not necessarily the case. So from with the Airbods program, the test chamber, it was shown that ventilation rate, in that particular scenario, ventilation rate is best, improving that, then mixing, and then both of them are far more effective than using screens. So screens can actually reduce the mixing in a room. Screens are more effective at reducing larger droplets, less effective at the aerosols because they can circumvent the screens. You need to consider it in situ with all the ventilation systems as well. And the screens could possibly increase the number of aerosols reaching a susceptible person. So this is a key element there. So what are the practical implications? I think it would be good to get guidance out there when not to use screens, not only when you should use screens. What are the geometries and ventilation systems which provide that guidance? Are you trying to protect the staff, the public, both? You can do some calculations and measurements to support the designs, but it is challenging to cover all the different scenarios. So perhaps there should be a case study library that you can feed off. Again, not as all as it seems. You think opening the window, that reduces airborne infection risk. So this is a CFD study, a slice, say, a metre above the floor of a open plan office. And there's this, I'll talk a bit about it a bit later, but this metric, which is showing about lower and higher risk of airborne infection. So opening in a small perimeter office, if you open the window, that had a massive impact, reducing the risk of airborne infection. But what it did in the open plan office, it actually increased the risk. There was a whole series of windows across the whole of that facade that were opened. So the question is, if you've got a large densely occupied open plan room, how does opening a window impact the air movement and mixing? And how's that estimated locally? Because that could actually increase your risk. What are the easy wins to increase airborne infection resilience, such as moving furniture? Should we be generating breathing channels? So compliance versus performance. So when we talk about natural ventilation, there's guidance normally says nat vent's best, then mixed mode, then mechanical ventilation. So this is, we normally think of a flow rate as a value. This is just a indication of what flow through two different types of windows look like. There's a top hung on the left, parallel on the right, both with a 100 mil gap. And indoors, in the model, inside and outside is exactly the same. And the only thing that's changing is the window configuration. So we're not really that interested in the window area, but we are quite interested in the open area, and even more interested in the pressure loss as you go from one side to the other, and this thing called effective area, because that includes a pressure loss coefficient, and that for any given pressure difference, that drives the flow through the window. But if you've got no air temperature difference and no wind pressure, you're going to get no flow. There's absolutely nothing to drive it. So when we talk about compliance, what does full annual compliance actually mean? If you say you need to guarantee 10 litres per second per person, well, there'll be times that that's not actually going to happen. And how do you police it? It's really difficult to police that. So, should we start moving in naturally ventilated buildings or modes of operation to exceedance-based time targeting, where you've got set climate and wind profiles, and that starts to determine the times that you're not meeting those minimum targets. Mechanical ventilation, quite often we define a mechanical ventilation rate. This is a slice through a building where it was a food production facility, raw dough, wanting to have a good cost formation. The idea was for less horizontal air movement, carry distance before adequate dilution. That's the same with the workers there and the spray from them talking onto their neighbours. And when we look at the air change efficiency in the lower half, these were separate systems. High air change rates showed a high air change efficiency, and low in the space that we were designing with the high vertical air movement component. So you would have thought blue's best. But when you look at it's a sort of simple dilution model, looking at what would translate into minimum horizontal distance that's safe, we're seeing in the top half it's a lot safer because of that vertical air movement. And in the mixed zones with much higher air change rate, you need much greater distances to be safer. So within this design, the optimizing the performance included air quality and energy usage and gave us 4.7 air changes. The hygiene guidelines asked for 5 air changes, so the minimum. So if compliance trumps performance, the only acceptable design is actually suboptimal. So quite often I look to promote performance-led design because you end up with better solutions, but we need to understand how that fits within our compliance metrics. So what's the best time and place for airborne infection reduction? This was at an event looking at a operating theatre with and without a, without on the left and with a device. And the logical thought process should be what's our operating scenario? So for example, what's the weight, acceptable weight between patients? Then what can I do with my surface mounted ventilation system? I know I'm going to have people and equipment in there. They're going to extract the flows, their heat loads as well. They'll be reducing the ventilation performance. So what's the best practice and practical air cleaning device location? In the middle of the room might be the least practical, but the best in terms of performance, or is it a stagnation area? And then what other performance specifications? So it kills 99.9999999% of all known germs. In Airborne, as I suggested once, that we debate the number of decimal places we see in assertions on kill rates. This is one that's commonly seen from, talked about in the air cleaning guide, 99.9% of viruses in 2 hours. So ultimately, we'd like to understand what are the tolerances, accuracies and sensitivities, not just on the surfaces, but also in the air. We'd like to understand what's the combined surface air treatment strategy, which is best. Think about capture, removal and inactivation. Think about if we got a large volume space, for example, what the natural biological decay might be. And also, what are the kill rates? And I'll talk about that a bit more on the next slide. So there's potentially an awful lot we should be thinking about. So this is just a question that this raises. So to what extent can a surface cleaning strategy be reduced by installing a highly performing ventilation system? I don't think we're thinking along those lines. Yeah. And this reanimation I mentioned of virus-laden particles off the floor and into the air. Does the ventilation system actually promote that? Is it good that it pulls that straight into your extract system? So testing kill rates. So by far we see this, which is a test chamber filled with an aerosolized pathogen at the start, T0. You switch your system on and at T2, you take the sort of concentration then, and the kill rate is a function of the concentrations at those 2 times. This is perhaps what we should be looking at quite a bit more, which is a fixed flow rate system where you're running it through a duct. You switch your system on and you look at the concentrations differences between one position and another position, and these can start to generate some flow performance rating curves. So the challenge for us is to align the test methods with reality and provide modelling performance data. Test 1 doesn't really give us modelling performance data. It doesn't tie in with periods and systems that we're putting in there. And then there may be the actual specific risk that may not be known. Surrogates are used, and it may be challenging to choose an appropriate kill rate. What are those targets if we're actually, if they're undeveloped? So I mentioned the podcast earlier that mentions that single pass or standards may maybe start to be thought about, but also would need the testing facilities to be developed. I saw one paper that did this. There's a lot of kit to try and actually make that happen. So we used proxies and banding. So you might be used to this sort of air quality table using CO2. This was adjusted in airbods to air quality bands where you may have some infection risk. So when you got these sorts of bands, should we look at 801 parts per million? It's just outside category B, so we should be aware when people are exercising and singing. Should we be looking at 2001 parts per million all the time, because this is what that band is saying? Well, the bands don't actually work like that. When we think about CO2 sensing, for example, the best you can ever get is 30 parts per million, just about. That's what we had in Airborne. Quite often it's 50 parts per million or more than that. And these limits should be used to trigger discussions on severity. And then we think about what the role the banding has to play, what the appropriate responses are to those limits. So they should be clear, and that should be based on all the wider risks that may be involved. So talk about our toolkit: calculation data, points and variables. We've got analytical data, single data points, dynamic thermal models, tens of zones, CFD models, millions of zones. So, this is just showing the two-zone dynamic thermal model in blue, single point on analytical and CFD, and there's loads of different physics in there. If we look at the measurement data points and variables, again, if you've got a backpack that's moving, you're not going to be using a backpack that's moving in a test chamber, because you'll be influencing the flows. But in a test chamber, you're going to have these sort of tripods and hang-ins data. There's a whole host of different spatial resolutions as well as actual variables in there. So if we look at our, in summary, our calculations and measurements, think of them as Venn diagrams, and then as typical times. There may be a static time for CFD and analytical models, hourly on dynamic thermal models, or sub-second in measurements, depending on what you're doing, if it's fixed on a wall or not. And there's a whole host of different data types as well, depending on the science and what we're looking at, spatial resolutions, behaviors, people moving, opening windows. We quite often join thermal models, dynamic thermal models and CFD, because surface temperatures can be fixed and the CFD does the air movement in seconds. I've talked about accuracy, tolerances, simplifications, validation as well, and verification. What are the common touchdown points? But there's no single calculation or measurement method that covers all of space and time. And the question is, what do we mean by correlation? Where are those touchdown points? So I do need to speed up a little bit, probably about 5 more minutes. We've got environmental surveys. So there's obviously a strong relationship between outdoor air occupancy, that's just numbers and activities as well, and airborne infection. We know CF2 is a proxy. It's not measuring airborne infection, but it's showing poor ventilation overcrowding, which may lead to increased levels of airborne infection. Ineffective dispensers, microbiological sampling. This is more pathogen specific, needing expertise, but it can still be used to identify transmission routes and risks. But on the measurement side, it needs an existing building to monitor in use. You may only be able to tweak a ventilation system, do a small change in operation. And also there's calibration for long-term sensing. The analytical models, this is showing a mass balance. We talk about this quite a bit within the Airbods, and it's about a single effect with the same viral loads comparing against other scenarios. And there's a question about what we can influence. We can influence the occupancy emissions, the ventilation side and the filtration side. If we look at the sensitivity test, there's this sort of output for a 20-person office with the high and low limits, occupancy, architectural design. So there's all sorts of overlaying of these types of very quick studies or reasonably quick studies, and it relates to the resilience in different scenarios, but it focuses on the long-range airborne exposure. And it's subject to limitations, as all of the methods are. We can look to the multi-physics. So this is a thermal model with advanced controls looking at CO2, PM, and various other aspects. You can do occupant behaviour. Perhaps may only go down to 6 minutes. So if you're going to flush a room with a window. 6 minutes might be the minimum. So you've got all these sorts of areas that you can include within the model. And we know that we're going to be doing more of this modelling. And there's new overheating guidance where that may bring some more of these models in that we can adjust. And also digital twins supporting live health and safety controls. And then the final part is CFD models. So this was a framework that we pulled together in the B&E paper. It's got a CFD focus, but it has thermal modelling working alongside it to design scenarios, provide surface temperatures. It's got a metric looking at different areas, different sensitivities, different viral loads. But you can actually look at what is the effect of moving this supply air grill or a desk. What are the different mitigations? And it might have different mitigations from mixed zone methods. So a possible future may look at being less dependence on the infector and susceptible person locations and quickly switching between diseases, not actually rerunning the model, but just the outputs. So I pulled this together in 21, looking at spatial, temporal, building science disparities, trying to put in one slide all the areas of measurements and calculations. And I picked out some of the points, so you can listen to that in the event. But I wanted to think, what do we learn since the airbots? So we know it's really hard capturing in measurements the emission rate, droplet distribution and various gradients, capturing air movement with time location recording on the equipment side beyond CO2. There's a big debate about using these mixed zone models on the analytical side, perhaps over-interpretation on spatial aspects. Then there's the verification and validation on the thermal modelling side and how you might be able to integrate some of those analytical models. And on the CFD, quite often they run without surface temperature models, but there are surface temperature effects and thermodynamic effects. And bringing in some of the advanced biophysics is something that is going to come. So we need to make hay while the sun shines. We're in a lull between pandemics, many of us would think. We learned a lot through the recent pandemic, perhaps that we could reduce by up to 50% against poorly ventilated spaces through ventilation. And we know ventilation matters in many, many different areas. You know, it's just something that really should be at the top of the tree in our thinking. But this holistic value is something that we're not very good at capturing. We know that for every pound we spend, if we're looking at more things, it may actually show an increased gearing of that investment and lead to improved decision making. So airborne infection assessments in the future, what might that look like? Well, standardization, integrated into air quality and the staging as well. Do we use some of these analytical models at a very early stage, helping your system selection? Then you run your thermal models, you highlight where you've got high CO2 levels, and that might, for an important space, that might lead to CFD models afterwards. We need increased confidence in the killer products integration, what they're performing at. This mix of male, female and child, talk about space-time occupancy targeting rather than just a flow rate. Validation, how we simplify that for industrial usage. I've talked about those aspects before. Sector-specific guidance. Should we have common libraries based on space and system? There could be some crowd simulation, breathing and people dynamics within there, people movement models, better educated and highly skilled designers and operators. Finally, what might compliance look like? It may be something like this. You submit for an office, shows you when it's unsafe to operate and you need to change or improve your ventilation performance. There might be a where you can operate up to a certain community infection rate, and then where you can't operate up to, where you can operate without any limits in the so up to certain community infection rates. And we talk about the BODS tool as well, which again might be something, a route to go down for compliance. This is the final slide, just some additional thoughts. So in Airbots, we have exports with a whole host of different skills integrated into one team. So that is a big challenge for industry. Quite often we're quite often siloed in what we do and in the way that we procure services. That's a significant barrier. How can we ensure the lessons not learned from SARS-2 and 3 aren't repeated? So, we know that there's a lot of navel gazing going on at the moment with the COVID inquiry. I'd hope ventilation was a key part of that. And we also know that we should be learning from what we've done as we move forward. I've talked a bit about competency, how we make sure we can be competent, because there is some real challenges on the health and safety side when it comes to a pandemic. And then the value of research in a pandemic is lower than if completed beforehand. So we talked in the pandemic about flattening the curve. Well, can we flatten the curve on effort and funding so that we can actually do a lot more work so it's ready for when there's the next pandemic? So that's about making hay. Ran over a little bit.
Okay, thank you very much, Darren. There's a question from on the slides, that getting a copy of the slides. These will be put on the CIBSE Healthcare website with all the details that you've seen there today. We'll try and get that out in the next week. Next question is from Mohit, was what are good CFD software what is a good CFD software to model aerosols and study its prevention measures in aerosols in buildings, that is? Have you got any recommendations?
At the end of the day, software is only as good as a user. Any single software package is a Navier-Stokes solver. If it's got a Lagrangian model, then you can actually do the actual droplet movement as an individual parcels of droplets of different sizes. But you can do gas clouds as a species. So every single software package should be able to handle it. It's all as good. And just, it's about using the manual and speaking to the vendors. If you're paying for it, if you're not, then there's communities out there to help you.
Okay, who else got on there coming? How the AHI index made, for instance, how was the range identified high and low?
So the REI index. So I suggest you go onto the Airbod's guide, and there's links to papers. Ben Jones at Nottingham University. There's just going through the guide that will get you very, very quickly to the papers. And but you saw the sort of mass balance thinking behind it. I didn't want to put equations up on this presentation because there's enough to get through.
So Gavin Teo asked, can you explain slide 10 in regard to what are the W, X, Y, and Z?
So that was just an indication that there's 4 different types of flows. One being the central system, central plant W, one being the air cleaning device X, one being the recirculating air handling unit being Y, and the other being the infiltration exfiltration Z.
Okay, hopefully that explains that one. Is there any allowance for future climate change scenarios in the models? If people's behavior changes due to overheating, will this also affect infection control?
Yeah, behavior is massive. In building simulation group, we just put a proposal in to start to understand occupant behavior. So a few years down the line, it might have a dynamic thermal modelling.
What about the future climate change?
At the end of the day, what do we mean by future climate change? If you're going to include urban heat island effect, if you include a 2050 medium scenario or 2080 medium scenario, that would translate into a elevation in an outside air temperature. And your system is all about balancing a system, but ultimately energy is going to drive a lot of how we incorporate airborne infection reduction, in particular winter. So modelling will really help us to understand that more, but we're not there yet. Huge amount of work to be done.
Can we develop your research for a HAZOP research study in a contaminated oil mist workshop for staff? So basically looking at simulating other scenarios and do that.
Well,
hazards.
I don't know the hazard research study, but I think, you know, if it's a fluid and you've got gas and aerosols in there,
Yeah.
you can model it.
Yep.
Well, I think we're doing some sort of modelling, and the you know, getting your it's a validation of your models that you put it in, because so many things affect it. We've been doing something for theatres, and it quite markedly, even the you know, change the position of the anaesthetist can have such an effect on your flow rates when you took laminar airhoods. It's always it's indicative. You can never say it's a yes or a no, and people tend to want yeses and nos. I think that's one of the things that we found.
So validation is always asked whenever you're at CFD conference, as well as turbulence. And validation is a key thing. Validation doesn't mean measurements are right, computer simulations are wrong. All it means is that giving two different sets of answers, and you're looking at what the differences are telling you between those two different sets of answers. But what I think I showed here is that the touchdown points are few and far between.
Yeah.
So you need to think beforehand, you do any calculations or measurements about where your touchdown points are in terms of data resolutions, temporal resolutions, all these variables, and then see whether that gives you more confidence in any of the different approaches, being measurements or calculations.
Another question was how to control infection risk in a space. Can we use CO2 as an index?
Well, CO2 is the proxy for saying that you've got poor ventilation and or over occupancy.
Yeah.
So it's not an index, it's a indirect it's an indirect output that says that I may be in trouble here. I need to look in a bit more detail. And then I would say, you know, we've got a whole toolkit of different ways that you can look at things in more detail.
Another one from Mohit was, in Delhi, India, the air quality index during winter reaches 500. Is it possible to provide better indoor air quality when the outside air is that bad using ventilation and air filtration techniques?
Like anything in life, I think it's about getting the balances when you can.
Yeah.
Also, you know, one of the things, you know, we're in a climate and air quality crisis. You know, and do we cool our way out of you know, heat gains to our environment, and or do we do naturally ventilating for as much of the year as possible, and then use mechanical for lopping the peaks? So that's one key balance that we've got to understand, and it might be in somewhere like New Delhi that you do naturally ventilate when the days allow you to naturally ventilate, rather than driven by temperature. Yeah.
One of the other ones that you mentioned early on was we have these different methods of looking at ventilation within the space, from air changes per hour, litres per second, or litres per metre squared, and those are three different sort of parameters. Do you think we should be standardizing, or CIBSE should be standardizing and saying, right, go forward with this is going to be the way to do it? Is going to be, you know, I don't know, is it litres per metre squared? Is there a good one and a bad one in those three particular methods of indicating ventilation within the space?
Just, I think, a massive risk involved with what we're doing at the moment. And you can't expect a grad +4. Sorry if there's a grad +4 online. Using as an example, there are very few people that would have. You don't read a standard. You dip in and you dip out.
Yeah.
So what would be great would be a tool that, if you say I've got an operating room with this type of system, then press a button and all the standards tell you what they're saying for that particular room and system and occupancy level. I think that would be a lot better, because then you'll be able to go, well, I don't believe that one.
Yeah.
But I might have to do the part F because that's a approved document and that's supposed to trump all. If it doesn't trump all, I'm going to have the, hopefully, performance-led arguments to say I'm not going to follow that because I've got a better system I've designed, and then that would have to be signed off.
Okay. Another one just come in on from the audience was how to conduct validation for CFD models in airborne infection dynamics. Is there a benchmark?
Yeah, we've got a page on the Airbods guide where we within the test chamber we took some measurements and we did some CFD, and we show where we validated. I would call that, you know, anyone that says they're doing perfect validation across all the various aspects, I would really want to understand how they're doing it. And there are some really good kit that fires lasers in terms of what airflow is doing at any point in space, in terms of a vector, and you could tie that in potentially with a CFD vector, because the starting point is what's your background airflow pattern. If it's not doing the same thing, you may just be lucky getting the same numbers out between your calculations and your measurements.
Another one from the audience was, does the 10 litres per second in building regulations need to be upgraded to a higher rate due to the pandemic outcome? I think BCO have already done that, haven't they? So,
again, if you look at that podcast on 241, they talk about 20 litres and 30 litres per second, and how people aren't going to be happy with that. You know, it's, you know, it's just the happened this pandemic really. We're at the very start of what needs a lot of work to get to where we need to get to.
And I think, well, you know, obviously the implications of going, say, from 10 litres per second to 16 litres per second or 20 litres per second is so great. Someone's got to start making those moves, because that's got an implication on cost and energy all the way through. So we need to have that debate to work out where the system should actually go.
But my argument would be that you'd want to go into the depth of 241, and understand through the equations why it's telling you to double the flow rate. And is it based on mixed zone systems? Is it based on a CFD background to drive it? What is the background of the thinking behind those judgments, which are made in committees?
That's obviously one for the future of CIBSE to get their teeth into. So that was it, 59. I think if that's all the questions from the floor, I think we will call an end there. Thank you very much for all the audience questions, and thank you, Darren, for the presentation. Thank you.
Thank you, Darren.